Um, my name is Avik Sengupta, and I lead the engineering of a company called Julia Computing. And Julia Computing is a company that's formed out of an open source programming language called Julia that I hope to talk to you today about. And I will spend the first sort of 10 minutes talking about Julia in general, what makes Julia a good language, and then move on to talking about how we can help do machine learning and artificial intelligence a little better with this language. So that's sort of the structure of my talk, and hopefully we'll get some questions at the end, right? So the first question is, why Julia? Why do you need a new programming language in this decade? Why in sort of, 50, 60 years since the first programming languages were developed, why do you need a new programming language? And I think the answer to that question sort of relies on the experience many people have writing analytics code in production, is that you have a team of people, they are called sometimes data scientists or quants and banks, who sort of develop models, right? They develop models in R or SAS or these days Python. And very often you will find that when you load those models to production, when you want to run those models on large-scale data sets, you end up having to rewrite those models in C or C++. And this is something that's quite a common workflow in many industries, banking in particular, but other than in pharmaceuticals, for example, that's something that's very common as well, that you have these two sets of teams who are doing the same thing, but in two different languages, who usually don't talk to each other, who have different skill sets, and who sort of write or who approach things in different ways, right? Between this team of analysts or scientists and this team of programmers. And what Julia aims to do is combine these two worlds, that you don't want to write everything twice. You don't want to use two languages, a high-level language to write your model first, and then a low-level language to run in production, right? So this is something that we call the two-language problem, as just a name of this experience that I'm sure many of you have had. And what Julia aims to do is to solve the two-language problem. And how do we do that? Well, the idea behind Julia is that Julia is a high-level dynamic language. So you write Julia as if you are writing Python or Ruby or even JavaScript. There are no types. It's easy to write. A few lines of code goes a long way in Julia, right? So it's a very high-level language. But typically in computer science and programming, you say that a high-level language is always slow. If you want performance, you use a low-level statically compiled language. You use C or C++ or Fortran, and that's what you need to do for speed, right? A dynamic high-level language is always too slow. And what Julia aims to do is prove that that is not the case. So Julia is a high-level dynamic programming language that gives you the performance of a low-level language. So you code as if you're coding Python, but you get the performance as if you've written it in C or C++. And that's a combination that's unique to Julia. And that's what we think makes Julia such a great language for different kinds of numeric and scientific programming, including machine learning, right? Julia itself, as I said at the start, is an open source programming language. It's sort of the core community grew out of MIT in Boston, but it's now spread over the world, and we have a large community of, I think, at least over 250,000 developers who have downloaded and used Julia. And that's a worldwide community that, in Bangalore, there is a large community, including a Julia Computing setup, for example. And there are people from, in fact, all continents. The last JuliaCon, we had somebody from Antarctica, so we said, it's really all continents. So it's a large, diverse community. JuliaCon happens every year, which is where the community comes together. We congregate in MIT last couple of years and Berkeley this year, and next year we're going to be in London. And that's a large conference with over 75 talks that just gives you a sense of how big the Julia community is today, even though it's, as I said, a relatively new language, right? So that's the community, but there's also a lot of traction in industry, right? There are people using Julia in production, moving real money, doing great things that are actually moving the needle for the companies that use it, right? And I'll talk about a few examples very quickly, just to give you a sense of what people are doing with this language right now. Julia Computing as a company, as I said, has been formed to create products and services around Julia. Even though the language itself continues to be open source and will be open source, you can just download it and use it. Julia Computing provides some tools, some products and support on top of the language, right? Right, so a few quick slides talking about the use that people are making of Julia in industry, in production. Aviva, some of you may know, is a large British insurer. It's, I think, the biggest insurance firm in the UK at this point. They use Julia to calculate all their risk models. These are complex Monte Carlo models that they have found are 1,000 times faster than what they had before. And these models are, again, written by the actuaries. They are not rewritten by programmers from a high-level language to a low-level language. These are models written by the actual actuaries, the actual risk analysts, and they found it, as I said, 1,000 times faster than what they had before. So you can imagine how much money they have saved using Julia. The New York Fed, which is sort of the central bank in the US, like the RBI, uses Julia to do econometric modeling. Again, these are very large models that simulate the US economy, and they have published lots of papers on how they use Julia to do these sort of modeling. The Federal Aviation Authority in the US, the FAA, they are the regulators for all flights in the US. They have a system called the collision avoidance system that all airlines are mandated to have. Every airline needs to have a collision avoidance system in the aircraft so that they can sense when there is another aircraft nearby. And the FAA provides specifications for this system, right? Currently, the specifications are sort of a few thousand pages of text. They are big binders that are sent to the manufacturers of these aircrafts. The next generation will actually use Julia as the specification language. So instead of specifying in text, these things will be specified in a Julia program. And that makes the specification much more accurate, right? You can imagine that. Instead of writing pages of text, they write code. But also, the code itself is then, the code for the specification itself is used to test that, right? So you run simulations on the specification, millions of simulations that take days to run to test that specification. And Julia is a language, as I said, that is both high level and fast, and in a use case like this, it's perfect. You can imagine you couldn't do something like this in any other language. It would either be too slow or it would be too complex to write specifications in, right? There are lots of use cases in pharma. There are people doing sort of genetic analysis, and there's a Julia package that does something similar to a package in R, and that's again 1,000 times faster, at least than existing packages in R. So again, you can see the speed is really huge. Celeste is a very interesting project that we did in collaboration with Intel and a couple of other universities. And this is a project that is probably the biggest machine learning algorithm run in academia at this point. This is a project that takes all the images taken by telescopes, the last 30 years of images, photographs taken by telescopes across the world. And what it does is tries to infer the position of stars from just these photographs. So instead of having to manually pinpoint what the coordinate of each of the stars are, it computes that from the pictures. And as you can imagine, there are millions of stars and billions of pictures, or billions of stars and billions of pictures. And this is 30, 40 terabytes of data. This ran on 650,000 CPUs on a machine called Cori, which is a supercomputer in the US. And this ran at a petaflop speed. And this is the first time that a dynamic language has done a petaflop. Typically, if you want to do things at petaflop scale, you are basically limited to either assembly or Fortran or C, right? That's your only option. You couldn't get to petaflops with dynamic languages, but now you can. And so this is quite a unique project that we did, right? So that sort of hopefully sets up and gives you a sense of what Julia is and what it can do. Let's move on to sort of the crux of the talk today, which I'm sure most of you are more interested in, which is what does it bring to machine learning, right? What does Julia bring to machine learning? And so there are, all of what I said before about being fast and dynamic sort of brings itself to being easier to use for machine learning. And so machine learning has its own two-language problem, right? Which, if you've used any deep learning toolkit, TensorFlow, for example, famously, there are a lot of the innards written in C++, but there is a Python API around it, right? Which makes it easy to use, that's true. But yet, sometimes those innards leak out, right? And you're sort of struggling with, is this in Python, is this in C++? I'm writing Python, but the thing is actually executing in C++. How do I debug it? And all these questions come about when you're dealing with two languages. There is also another aspect to this two-language problem for machine learning, which is that each of these deep learning programs have their own sort of structure and the thing that they do very well, right? So Keras, for example, is very high level, right? It's very easy to use. It's got these high-level models, a couple of lines of code, and you get a model and do a prediction. Torch, on the other hand, is very flexible, right? You can do everything. You have to do everything manually. You set up your model, but you'd have to write a lot of code. And it's very difficult to mix and match these approaches with machine learning libraries today, right? If you want to start with a high-level model and then you want to dig down into the depths of a model as you iterate with data, that's difficult to do. If you start using Keras, you can't go deep. If you are starting using Torch, then you have to start writing large-scale models, right? And so what we think you should be able to do is go as deep down as you want. You start with a high-level model, but dig down as much or as little as you want. And this is enabled by having a high-level language in which you can implement the entire stack. So you're not transitioning language boundaries as you are digging into your model or trying to get more flexibility from a certain toolkit that you're using. So that, I think, is sort of the key message today, which is that this is what Julia enables you to do. And I'll show you a few examples of what I'm talking about in a little more specific fashion. So as I said, so what Julia allows you to do is create models or work at different levels of the stack. You can work at the mathematical syntax level where you have a paper that you're trying to translate. You want to worry only about the mathematics. You can work at that level. Or you can mix and match, or you can go deep down and dig into sort of working with the data, working with each field, seeing what your feature matrix is, doing dimensionality reduction on the feature matrix before you move it to a deep learning model. And all of that, you can mix and match your approach of what layer you're working on. So as I said, I'll talk a little more more specific about what you can do with that. But before that, quickly, some examples of things that people have done with Julia as pure Julia models. A friend of ours has done this diabetic retinopathy, which is using machine learning to predict eye disease from images taken in the camera. This is something that they are publishing a paper on that they're actually trying to build with a set of eye hospitals in Bangalore. This is a blog post, if you're interested, search online, that we did about doing neural style transfer in Julia. And that's, again, just a few lines of code that can use this existing model in Julia. Now, I said about digging down and digging down into different levels of abstraction. If you do the style transfer, you get a model, right? You can get these models in Python as well, or TensorFlow and C++. Just do a Google search of style transfer models. You will get many such models. But the advantage of having a high-level fast language is that you can then build on top of that. So if you have a model and you want to do this on a movie, right? What do you do? In Julia, you can just take each frame and distribute it across a cluster of 1,000 machines, right? And that exact same model will work on one machine, or it'll just parallelize itself with 3 lines of code like this. and run on Azure or AWS on 1,000 machines. And that's the power of having layers that you can build on top of each other. Right. So coming back to what I was talking earlier, right, about the levels at which you operate your machine learning model. The first is mathematics, right? A lot of these deep learning models are a lot of matrix mathematics, and you want to be able to write the mathematics as if it is mathematics, right? You want to take a paper and want to copy it into your code without having to translate the mathematics into a long 500-line program, right? And what Julia lets you do as, again, a high-level language is write mathematics as if it's mathematics. So for example, a simple feed-forward network, this is sigma xs star w, which are the weight, the w is the weight matrix. And again, this is a star b. That's the same syntax that you write in your mathematics. You can use that same syntax in Julia, right? So that's one. An LSTM, which is sort of some of the more complex machine learning models. You can see on the left, I have an extract of the original LSTM paper. On the right, I have the extract from the paper. On the left, I have the Julia code. And you should be able to recognize one from the other, right? They do look similar. And that, again, is the power of having a high-level language. As I said, you can do mix and match approaches in Julia. You can compose all of this together, right? You have a model, you want to define your own gradients, right? Of course you can do that. You don't have to dig down into C code inside TensorFlow to change the way your gradients are calculated. It's all in Julia. You can combine all these layers. So for example, this is a high-level API that we have in a deep learning model called Flux, which just chains an input layer to a fine layers and a softmax layer, right? Which is probably the simplest deep learning model you can have. And this is just 4 lines of code to define your own. But the important thing is not just that it's little code, it's also that you can dig down as you want. If you want to change the affine layer to something else, it's just Julia code. It's just a loop, right? It's just a loop running over 2 arrays. That's all that it is, and you can do that, right? You can take these high-level models, you can then move them to TensorFlow to train them if you want, or you can keep them in Julia, and I'll talk about that in a little bit. But also, if you love TensorFlow, right? And lots of people do. TensorFlow is obviously by far the most popular deep learning network around here. If you use TensorFlow, you can use TensorFlow from Julia. And what's the advantage of using it from Julia rather than Python? As you can see, the code in Julia looks much simpler. You don't have to say tf.matmul if you want to multiply 2 matrices. You say a star b, because star is the multiplication operator, right? You don't have to do tf.loop, tf.while loop to do a loop. You can just say a for loop or a while loop, because that's what the language is. So you can use language constructs naturally without having to sort of learn a completely different API to do things that every programming language should be able to do. So yeah, use TensorFlow, but you can use it from Julia. Finally, you have a lot of machine learning work, as I'm sure you've heard all day. A lot of it is before the model starts, right? It's about cleaning the data, loading the data. And here, this is just pure programming speed that matters, right? You don't care about training on the GPU. You just care about loading a large CSV file, maybe across machines, because it's too big to load on one machine. And as you can see, this is a chart that's on our website. Julia is almost as fast as C for a lot of these basic operations, right? And so that helps, and that's powerful in what you can do. In sort of all the pre-processing that you do, you can do quickly. Finally, what Julia gives you the ability to do is write Julia code and run them on these accelerators. So in Julia, for example, we can generate code to the CPU, the Intel CPU, which is the standard that everybody uses. But you can also generate code for the Knight's Landing, the Xeon Phis. You can generate code for the GPUs, right? You can write pure Julia code that gets translated by, without having to write CUDA-C, which if any of you have ever written CUDA-C, that's not something that is the most productive of languages. So here you use a high-level language, and that automatically gets compiled to either Intel CPU and run it on your laptop, or compile it to CUDA kernels, run it on your GPU, or compile it to ARM and run it on your Raspberry Pi. Using one high-level language, you can target a wide variety of architectures quite easily, right? So